Okay, let's talk about titrations. So a titration is basically an experimental technique to do solution reactions. Um, so in a titration, we use what's called a burette. And so it's this long tube that has measurement markings to measure volume of one solution. And then we set that up above a flask. And so we have an Erlenmeyer flask and we put the other solution in the flask. Um, So in this, you've got two different solutions, one in the burette, one in the flask, and those solutions contain the reactants for the chemical reaction that is going to be performed. Um, and so you accurately measure that solution that goes in the flask. So you use some accurate pipette and transfer in a known volume into that flask. And then the burette, it's got that little valve on it, that stopcock, that you open that valve up and it releases the other solution into the one in the flask. And it allows those things to react. And you release it until the reaction is complete. So really, when you hear that term titration, it's just describing to you that, or trying to explain to you that you perform this reaction using a titration technique. And so you're using a burette and a flask. And so what you're doing is you're measuring volumes very accurately. You're not weighing out masses of things, and you're not weighing out the mass of products or anything like that. You're measuring these volumes, and then you're able to relate those volumes to concentrations of those solutions. And then relate them to moles of the solutes in those solutions. So in this, most of the time when people are talking about doing a titration, they will use the technical terms analyte and titrant for the two reactants. And so the analyte, that is the solution that we put into the flask, okay? Whereas the titrant is the solution that is in the burette. So don't let these terms scare you. When you hear the term titration, it's just a solution reaction. And when you hear analyte and titrant, they're just specifying which solution is where. And then with this, in addition to the reactants, you actually have a substance that is an indicator. And an indicator, that substance, you add it to the analyte solution. Okay, so you have that solution down in the flask. So after you've accurately measured volume and transferred it to the flask, you put usually a couple drops of an indicator solution into that. Okay, and so the indicator isn't a reactant in the reaction that we're trying to study, but it is a substance that changes color at or near the stoichiometric point of the reaction. Okay, and the stoichiometric point is when you have exactly enough of both reactants to perform a complete reaction, and there's nothing in excess, there's nothing limiting. Okay, and so basically the indicator changes color when our reaction is done. And so that way we know we can stop adding titrant to the analyte. Now, the terms that we use that relate to that stoichiometric point, well, the term that really is the stoichiometric point is the equivalence point. So sometimes people will talk about doing a titration to the equivalence point, or that the equivalence point is found when they've added this much volume of titrant. But when you're doing a titration, really what you measure is truly the end point. So the end point is when the color changes for the indicator, okay? And if you choose the right indicator, if you choose a good indicator for your reaction, then the end point should be the equivalence point or very close to it. At least to the accuracy we're measuring things, it should be the same. And so a lot of people will just interchange those terms. When you hear equivalence point or end point, think stoichiometric point. Think that means that my reactants are in the ratio that the reaction tells me, that the balanced chemical equation tells me that they need to be in. Okay, so that's all really your terminology that's associated with titrations. But in reality, this is just reactions of solutions. Okay, so if you're in the lab, maybe you do the titration and you collect the data and then you utilize it for calculations. But a lot of times we just give you the information and we say, okay, a titration was performed and this is what was measured. Okay, and then you're asked to calculate usually some concentration from that. Okay, and the calculations you're doing for any titration data are just going to be stoichiometric calculations. Okay, so it's really a stoichiometry or a solution stoichiometry problem. Okay, so I'm going to do a couple of examples, and the examples I'm going to do are acid-base titrations. So that's probably the most common type of titration people do, is they do a titration involving an acid and a base. So your acid and base, one of them's the titrant, one of them's the analyte, and you titrate it until they've neutralized one another. You can do titrations with other types of reactions, so like precipitation reactions, you can do a titration of a precipitation reaction as well. It's just most commonly we do them with acids and bases. So those are the examples we're going to look at. We're going to look at some acid-base reactions where we have titration data. So let's see, the first one I've got here is the titration of a 10 ml sample of strontium hydroxide. And I tell you that it requires 21.5 or 21.35 milliliters of a 0.75 molar acetic acid solution, okay? Meaning that's how much I have to add to get to the end point, okay? And I want to know the concentration of the strontium hydroxide solution. So first off, since I know this is a reaction and it wasn't given, I'm going to write the reaction and balance it, okay? So I have strontium hydroxide, which is SrOH2, because strontium is a group 2, so it has a 2+ charge, and hydroxide's a -1. And that's going to react with acetic acid, which is HC2H3O2. Okay, so it's the acetate ion with H+ on it. And then that's going to, those are all going to split into ions and swap partners. So the Sr2+ from the strontium hydroxide combines with the C2H3O2- from the acetate, or from the acetic acid. And so you're going to get SrC2H3O2 2, because you have a 2+ ion combining with a 1-. So they combine in a 1:2 ratio. And then the H+ from the acid combines with the OH- of the base, so you get water. And then you have to balance the reaction. And we're going to need 2 of the acetic acids, and that's going to overall give us 2 waters. Okay. Okay, so this is our balanced reaction. Now, the information we know is that we have 10.00 milliliters of strontium hydroxide, and we used 21.35 milliliters of our acetic acid, and it's a 0.75 molar acetic acid solution, and we want to know the concentration of the strontium hydroxide. So the concentration of that is what we're looking for. Okay. Now, just like a lot of other solution stoichiometry problems, you may notice, like here, you've got a volume and a concentration. Here, you've got a volume and a concentration. And so I know when you see that, a lot of people want to use C1V1 equals C2V2. But that, you cannot use that equation. That is a dilution equation. Do not use that. Okay, dilutions are just when you're adding water to something. We're not just adding water to either one of these. We're adding 2 different solutions to one another. So you need to do stoichiometry. So we're going to need to convert something to moles and then do a mole to mole conversion and then get what we want. So the acetic acid, we have enough information there to actually get moles. Okay, so we can get moles of acetic acid, and then we can convert that to moles of strontium hydroxide, which then we can convert to the concentration. Okay, so those are the steps we're going to go through. Now, it might make it a little easier if you rewrite these concentrations. So this is really 0.75 moles per liter of acetic acid. I guess that's the only concentration we have. The other one we're going to have to calculate. So that really is like a conversion factor. Okay, so it's 0.75 moles per 1 liter. So I'll use it as a conversion factor, meaning I'm going to start with the other number, the standalone number. That usually makes your life the easiest. So 21.35 milliliters. I can convert my volume to moles if I have it in liters. So I'm first going to convert that to liters. So I put milliliters on bottom, liters on top, and it's 1,000 milliliters per 1 liter. Okay, and that's my acetic acid. So I can convert liters of that solution to moles of acetic acid by using that molarity. So it's 0.75 moles per 1 liter. And then I can convert my moles of acetic acid to moles of strontium hydroxide. And that, once I have moles of strontium hydroxide, I'm going to be able to get its volume. So my mole to mole ratio there, I have a 2 for the acetic acid and a 1 for the strontium hydroxide. And so I'm going to go ahead, I'll calculate that, and then we'll continue. So 21.35 divided by, and this is supposed to be 1,000, divided by 1,000 times 0.75 and divided by 2. And so that gives me 0.0080006. That's more than enough because really in the end I have 2 sig figs. So I'll just go ahead and keep those 4. That's fine. So I have my moles of strontium hydroxide. Now I'm going to take those moles, and if I divide them by my liters of solution, I get the concentration. So 10 milliliters, if you convert that, is 0.01000 liters. Okay, I'm not going to write out that conversion. I'm just go ahead and use that from doing it in my head. So 0.008006 moles divided by 0.01000 liters. That's going to give me my concentration of strontium hydroxide that was reacted. I've got 0.01. Okay. I guess I could have done that in my head. And so I need 2 sig figs, so it's 0.80 molar strontium hydroxide. Okay. So that's a titration calculation. It is just a solution stoichiometry calculation. Okay, it just sounds like it's more difficult, but it's not. It's the same thing. Okay, so let's see. Let's do one more. So this one, we've got the titration of 15 milliliters of a phosphoric acid solution, and it requires 23.55 milliliters of a 1.18 molar calcium hydroxide solution. And I want you to determine the concentration of the phosphoric acid solution. So again, we don't have a reaction given, but this is a reaction between those two things. A titration always is a reaction. So if you're not given a reaction, that should be the first thing that you do, is write that out. So we have phosphoric acid, which is H3PO4, okay, and that's going to react with calcium hydroxide, which is CaOH2, and then what gets produced is, well, water from the H plus from the acid and OH minus from the base, and then some salt. And the salt that's formed is a combination of the cation from the base and the anion from the acid. So the cation from the base is Ca2 plus, and the anion from the acid is PO43 minus. So I have a 2 plus with a 3 minus. I'm going to need 3 of that cation and 2 of the anion. So it's Ca3PO42. And so that should help me with balancing. I put a 2 in front of the H3PO4 because I need 2 phosphates, and a 3 in front of the calcium hydroxide because I need 3 calciums. And then that overall is going to form 6 waters because I have 6 H pluses and 6 OH minuses. So that's my balanced reaction. And let's see, the info we know is 15 milliliters of phosphoric acid, which I'll go ahead and rewrite that. That's the same thing as 0.0150 liters, okay? And we have 23.55 milliliters of calcium hydroxide, which I'll go ahead and rewrite that. That's 0.02355 liters. If you prefer, you can write out that conversion, but after you do so many, you can do it in your head. Okay, calcium hydroxide is 1.18 molar, which we can rewrite that as 1.18 moles per 1 liter, and that's moles of calcium hydroxide. Okay. Okay, so that's all our given information, and I've rewritten them in ways that maybe are more useful. And we want the concentration of our phosphoric acid. Okay, so we should be able to get moles of our calcium hydroxide, convert that to moles of phosphoric acid, and then get our concentration. So those are the steps we'll go through. We'll use the given information to calculate moles of calcium hydroxide first. So we have 0.02355 liters of calcium hydroxide solution, and we can get rid of those liters and go to moles of calcium hydroxide by multiplying by the molarity, the 1.18, because that's how many moles are in 1 liter. And then we can convert the moles of calcium hydroxide to moles of phosphoric acid by using the balanced chemical equation. So a 3 with the calcium hydroxide and a 2 with the phosphoric acid. And that's going to give me my moles. I'll go ahead and stop there. So 0.02355, let's see, times 1.18 times 2 divided by 3. And that gives me 0.01852 moles. I'll just write all of that down because we're not done with the calculation yet. So we've got some extra sig figs there. And so I need the molarity, the concentration of the phosphoric acid. So 0.01852 moles divided by the liters, so divided by the 0.0150 liters. And that's going to give me my molarity of phosphoric acid, 0.0150. So that gives me, let's see, 1.24 molar of phosphoric acid. And that is our answer. Okay, so again, a titration is just a reaction between two solutions. And so when you do calculations from a titration, it's just solution stoichiometry.